We continue our work here in chapter 34. And this section is 34.3. We're going to look at the exact equation for the image, for objects and images in general, and what their magnification is for both of these cases. We're going to let DO, the distance to the object, and distance to the image, be the distances from these objects and images. And then we find this incredible formula that applies throughout all of mirrors and all of lenses, so it's of incredible importance, that 1 over the distance to the object plus 1 over the distance to the image is equal to 1 over the focal length. And the focal length is that position such that all light emanating from there would go to infinity, or conversely, all light coming from infinity would focus or go to that point for an image. The second formula that we have gives us our magnification, and the magnification is always the negative of the image distance over the object distance. And this is kind of common sense, because if we think of in what we do, if you think about the triangles that are involved, the distance to the object versus the height of the object and the distance to the image versus the height of the image tells us that this distance divided by this distance is going to give us our magnification. In other words, the height of the image divided by the height of the object. In other words, how high does that image appear relative to the height of the original object that we're looking at? And that can be smaller or it can be larger if we have reduced or enhanced magnification. We'll explain this negative sign and some signs associated with this later on. If we have a negative, then the image is inverted. Positive, then it will turn out to be upright. Now, to show that more explicitly, I'm first going to give you 2 examples. Here I've drawn out a concave mirror where the center of the radius of this, if I wanted to put a point out here, this would be the radius, meaning all of these points are equidistant from this radius. And by that first formula that we had, where we found that the focal length is equal to the radius divided by 2, that incredibly important formula, tells us that the focal length is going to be halfway between the mirror and the central point here. And now what we're going to do is we're going to put an object out here. Now, usually with lenses and mirrors we use an arrow, and this way we can tell what's up and what's down. And we put this on this central axis, as it's called, that goes through the center of curvature right over toward the mirror. And we'll stand an arrow up here and say, how does that arrow appear when we look at it in the mirror? There are 2 ways we can trace these ray diagrams. One way is we know that light that goes straight through the center will hit the beam over here and will go straight back up the mirror again. That's because this part right here is perpendicular to, this is tangent to, light that comes from the center. So light that comes through the center will go straight back up this way. So here's the one axis, and that will determine, in part, where this image is going to be. Now here's our image area, here's our object area. This is where it will appear to be. Now the second way we can always do this is we can start at a point here at the arrow and go all the way down here through the focus and let that reflect. And remember, if it goes through the focus, it's supposed to go to infinity. So this line will go straight out to infinity. And where those 2 cross, since both of them emanated from this point here of the arrow, both of them will go to this point, and the image will be like this. You can do the same thing along this axis for both of those 2 same arguments, and both of the lines, both through C and through F, are on top of one another, which means that the bottom of the arrow is on this axis right here. Okay, now how do we identify these different distances? Well, the distance of the object is the distance from the mirror, right here, distance from the mirror out to here. If it's on the left-hand side, it's taken as greater than 0. Likewise, the distance to the image is the distance from the mirror to the image. And when it's on the left side, as is this, the source side, then it will be greater than 0 also. If the focal length, and the radius therefore, are on the left-hand side, then we say that the focal length is greater than 0. Then we have 3 equations. First one tells us what the focal length is in terms of the radius. Second tells us what our magnification is. And the third is the formula that's universal that gives us our connection that we just mentioned between the distance to the object, distance to the image, and the focal length. Now, in this first case, I've drawn 2 here. This first one, I have the object located to the outside rather far, and when I do that, the image is going to be real, inverted, and reduced. Here you can see it's real. It's on the left-hand side. Anything on the left-hand side is positive and real. It's also inverted, and it's reduced in size. This is much smaller than this is. So when we have a large object like this pen that's well outside the focal length, which is right here, then these will all apply. We can figure out what these exact distances are and the magnification by putting in this formula here. Now we're going to turn to the second situation, and in that situation a mirror is just like before, right over here. But in this mirror I have of course again a spherical mirror. The focal length is here, but I've expanded this area so I could put the object down here. When I put the object here, you'll notice it's within the focal length. It is closer to the mirror than the focus is. So this distance object is still positive. But now I'll draw my 2 rays as I did before. One will start from the center, go to the point, and reflect back. We know that we have one line that goes from the center to the tip of the object, and we can extend it on out here, where it'll go to the tip of the image. This is going to be the image. This is the object. And another one that starts at infinity, hits the mirror, and goes to the focal length by this point, or likewise starts at the focal length and goes across the tip to this point here. What these 2 lines do when they cross is they determine where the object is going to be, both the position of the center and the focal length. And they indicate that the image is going to be back over here on the other side of the mirror, and you can tell it's going to be larger. In this case, we find that the image is virtual, meaning it's on the right-hand side. You could not put it on a screen. There's nothing really back here. This is imaginary. Although if we look at this mirror, we'll see it back there. It's really not there. Kind of like in a regular mirror, when you look at an object, the object appears to be on the far side of the mirror, but there's nothing on that far side of the mirror. You couldn't put a sheet of paper there and have the image shown on that piece of paper. So in the second case, when the object is within the focal length as opposed to being outside of the focal length, we find that the image is virtual. It's out here. It's upright rather than upside down, and it's enlarged. It's much larger. Again, these equations apply, and they apply in a situation where if I'm on the left-hand side of the mirror, then in fact the DO, DI, and F are all, if they're on the left-hand side, they're positive. If one of these is on the right-hand side, they're negative. Okay, that does it for our mirrors that are concave. Now let's take a mirror that's convex and look at the situation there. For a mirror that's convex, or shaping outward like this is like our situation where we're looking at an object in the garden that might be a sphere or something. When we take a tree or something out here, you'll notice that that tree always appears to be small and inside the globe that we're looking at. Our distance of the object is positive. It's greater than 0 because it's out here. Our image distance is going to be back in here, as we'll find out, so it's negative. And our center of this mirror is here, and therefore the focal length is 1/2 of the distance here. The focal length is going to be taken as negative in our formula, just like the image distance is. And the image we'll find is virtual, upright, and reduced. It's virtual because it's on the right-hand side of the mirror where you couldn't focus it. It's upright, and it's going to be reduced in size. Again, the magnification formula and the distance formulas with respect to the focal length are the same as before. To convince you of the ray tracing, imagine the ray of light leaves this point and goes straight to the C and then comes back. It must go over the tip of the image error. Likewise, if light came from infinity out here and went and hit the mirror, it must go to the focus, or a focal light must go up to here and out to this point here. Those two lines cross, giving us the position of our image, and this would be the size of our image and the distance of the image, which is taken as negative because it's on the right-hand side. Again, if the distances or the focal lengths are on the left in the real side, then they're going to be positive. If they're behind the mirror, then they're going to be virtual, they're going to be negative. And that's true for the object distance, the image distance, the focal length, and thereby determining the magnification. So this covers our formulas and the central concepts for both convex and concave mirrors. I point out if the magnification is negative, then the image is inverted. If it's positive, then it's upright.